Right, we'll move on to the tutorial on the portal frames now. And I've made some notes up for you. The 3-pin portal frames, a recommended textbook by P.S. Smith, 2001, Introduction to Structural Mechanics, that's what we've been referring to earlier. It explains in detail techniques for the analysis of 3-pin portal frames. Students should study the worked examples shown in the text, as I said to you earlier. And the samples printed in the workbook should also be studied in depth. The following 2 examples are presented, assuming that the student has gained a fundamental understanding by following the suggestions made in paragraph 1 above. And here I've taken a simple portal frame and done it the way that I would normally do it. I've got a point load up there, no horizontal loads, and I'm looking for HA, VA, HF and VF. The question is, for the 3-pin portal frame shown, determine the vertical and horizontal reactions at A and at F. So, taking moments about A for all the forces to the right-hand side of A. So we're going to take moments about A, taking all these forces into account. And what have we got? We've got a 10 kilonewton force 3 meters away from A. We have a vertical, a VF, at 12 meters away, going anti-clockwise. This one's going clockwise around there. HF, of course, doesn't figure because it passes through point A. There's no dimension, no arm. And I've spelt that out. Yeah? So we've got 10 kilonewtons by 3 meters, going in the clockwise direction, minus VF times 12, going in the anti-clockwise direction, plus HF times 0. HF passes through A. All of that equals 0. And when you solve that 12 VF, if you solve this, 12 VF equals 30, VF equals 2.5 kilonewtons. So bang, there we have the vertical force. We take moments about D, the next step, of all the forces to the right-hand side of D. So all the forces to the right-hand side of D, all these forces, VF and HF. That's what we're doing in this step. HF times 10, because the column is 10 meters high. VF times 6, because that's the horizontal distance to D, equals 0. Solve this, and substituting the VF that you worked out up there into this equation, there it is, the 2.5 kilonewtons, you can compute that HF equals 1.5 kilonewtons. As we said earlier, for horizontal equilibrium, HF equals HA. It must also equal 1.5 kilonewtons. So HA must equal 1.5. To find VA, we take moments about D to the left-hand side of D. So we want to find VA. So we take moments to the left of D, there. VA times 6 minus HA times 10 minus 10 times 3 equals 0. From this, VA equals 7.5. Can you check it? Yes, you can. The vertical reactions must equal 10 kilonewtons because that's what your vertical down load is. So VA plus VF, 10 kilonewtons. The portal frame is in equilibrium. And I've made a little note on the bottom for you to keep in mind. The above simplified method can only be employed in the absence of horizontal forces. So as soon as you have a horizontal force, you can't simplify it in that manner. So please keep that in mind. And here I've done a fairly comprehensive frame for your edification. I've got a frame A, B, C, D, E. It has a vertical force of 20 kilonewtons above that column, a horizontal force on this beam of 5 kilonewtons, and it has a uniformly distributed horizontal load from wind or whatever it is of 3 kilonewtons per linear meter, pushing that away. Now, what you must learn to do is, if you see the forces, the external forces on the frame acting in a certain direction, you can be pretty sure that these two horizontal forces will be countering those. So they run in the opposite direction to those two forces, as you can see. We haven't computed them yet, but you could assume that they were running that way, so that HA would be a positive and HE would be a positive and the other one would be a negative. Let me reiterate, I'm falling over my own feet. They're both positive, they're both acting from left to right, sorry. We could make the assumption that VE is going to have to be going down as a negative because these forces are tending to turn this whole portal over. So you could make that assumption and then you'd get your signs right, your pluses and minuses. This one is obviously going to have to be a vertical force to support this structure. So the question is, that's the layout of the structure, and the question is, find the reactions at A and E, those reactions. Number 2, draw a dimensioned thrust diagram. This is a thrust diagram. And draw a dimensioned shear force diagram. That's the shear force diagram. And quick part 4, draw a bending moment diagram, and there it is. And we're going to go through all these steps now. So we look at the horizontal forces first of all, and we've got -3 times 5, which is 3 kilonewtons per meter times 5 meters, okay, going from right to left, minus 3 times 5. -5, which is that force there, also going to the left, -5 kilonewtons, plus HA plus HE. And as I said at the outset, we're assuming that those two forces are going that way to counter these two forces. So they're both plus HA plus HE. Transpose, and you get HA plus HE equals 20, and I've called that equation 1. Now we look at the forces in the vertical direction, and I've said VA plus VE equals 20. Well, VA plus VE must equal 20 kilonewtons. And actually, if you subtract that from that, and those are the final calculations, you'll see that subtracting them does equal 20 kilonewtons acting downwards. But anyway, at this point, that's equation 2. We take moments around A, MA, of the whole frame. So we have -3 times 5 times 2.5. That's the 3 kilonewtons per meter times 5 meters times a half of 5.5 meters, because it's acting through its centroid, 2.5 meters from there, this UDL. That's that part of the equation. -5 times 5. This horizontal force acting 5 kilonewtons. It's a point load pulling the thing over 5 meters away from A. -5 times 5. VE, what we're saying is, we're assuming that it's going in this direction for the reasons that I spelt out earlier, and it is 6 meters away from there, -6 VE, all equals 0. When you solve this equation, you find that VE equals -10.417 kilonewtons. And if you substitute 3 into 2, you actually can solve for VA. So if you put -10.417 in there, you'll find that VA equals 30.417, and the signs are correct. Our assumptions from left to right are correct. So VA is 30.417, VE is 10.417. You add those two together, you get 20 kilonewtons. That minus that is 20 kilonewtons going down. You know that your assumptions are correct. Now we could take moments about C for the left-hand side. So we've got, I'm just getting off the page there, 3 VA minus 5 HA minus 20 times 3. So we're taking moments about C, and we've got 3 VA, okay, going clockwise around C, minus 5 HA going anti-clockwise around C, 5 meters away, minus 20 times 3, minus 20 times 3 equals 0. And when you solve those, you get equation 5, which is 3 VA minus 5 HA equals 60. You can now substitute 4 into 5, equation 4 into equation 5, and find that HA equals 6.25 kilonewtons. And if you substitute 6 then in equation 1, you'll find that HE equals 13.75 kilonewtons. As I said to you earlier, you'll see that the sum of HA and HE equals 15 plus 5, 20. There the proof is down at the bottom there. So moving on, we're going to look at the axial thrust. At A, the axial thrust equals VA equals 30.417 kilonewtons. There it is. That there is squeezing this column, or tending to crush that column. And there the diagram is. And that's constant, that crushing force all the way up to B. So that is a plus. Compression, squashing it, is a plus. 30.417 kilonewtons at the bottom and at the top. That's how you find that. So, and what I've said is this thrust continues to point B. So it continues up to point B. At B, the horizontal thrust in BD is HA minus 5 kilonewtons. So what you've got is you've got the force in this member there. You've got 6.25 kilonewtons horizontal thrust there. You've got 5 kilonewtons going that way. You're left with a residual, if you take that from that, of 1.25 kilonewtons, and there you have it. And that carries all the way through that member BD. You've got a compressive force of 1.25 kilonewtons. Right, we want to look at the thrust in DE now. So at D and E, the vertical thrust is VE, because that is the force that's pulling down. But because it's pulling down, it's in tension. It's actually pulling on this column. It's pulling it down. Why is it pulling it down? As I said earlier, because this whole portal frame is tending to sway over and fall over to the left. So you need a force at this foundation to hold it down of 10.417 kilonewtons. In other words, if you had this loading system on there, this would be trying to lift off the foundation. The shear forces, at A, the horizontal shear force is 6.25 kilonewtons. There it is, 6.25 kilonewtons, tending to shear the column off there. There it is. It doesn't vary as it goes up all the way to the top. You have a horizontal shear force of 6.25. I've said this continues to point B up at the top of the column. When you get to the top of the column, we look at the vertical shear force in the beam BD, and we have 20 kilonewtons pushing down minus the force pushing up, which is 30.417 VA. And you're left with 10.417 kilonewton shear. There it is. That does not vary as you go across the beam, right to there. It's still 10.417 there. And if we now look at the right hand at D, the horizontal shear force is plus HE minus the load. You've got plus HE, because this is plus HE, and this is minus 3 times 5 is 15. Okay, So you've got minus 1.25 kilonewtons there. Minus 1.25 kilonewtons is your shear force there. That varies linearly, and you all know this from doing beams, because this load there is a uniformly distributed load. It has a linear effect on a member, like this. And the shear force down at the bottom is this shear force there, 13.75 kilonewtons, and there you have it. So that is what your shear force diagram looks like. If you wanted to work out what your maximum moment on this column was, it would be at a point just over there. That's where your maximum bending moment would be in the column. So there we have the shear forces, and the only thing we're left with now is to work out the bending moment. At A, the bending moment at A there is 0 because it's a pin. You can't have a bending moment at A. And the bending moment up here at B is merely this force times that distance. 6.25 kilonewtons times 5 meters gives you the bending moment there. Okay? 31.25 kilonewtons is the bending moment. Now you'll remember at the outset of the lecture today, I said that where these joints are stiff like that, the bending moment actually transmits right through to the other member. And that's why these two bending moments are exactly the same. Whenever you have a stiff connection like that, where you have a joint like this, and it distorts due to a force pushing on it like this, it does this. And we assume that that angle remains at 90 degrees, the same as that one there when it distorts. So please always keep that in mind. So at A, the pin bending moment is 0. At B, the bending moment is merely the horizontal force times the distance, minus 31.25 kilonewton meters, which goes up into member BD as well as 31.25. As B is a rigid joint, this moment is transmitted into BD, and that's what I've just been going on about. The moment at C equals 0, because you can't have a bending moment at a pin. You can't have a bending moment there, so the bending moment at this point there is 0. And because there are no other loads acting on this, you end up with a straight line going straight through there like that, because there's no forces changing the moment. So this 31.25 goes along and diminishes until it passes through that point, because there's no moment at that point. The moment at C is a pin joint. At D, the bending moment is, we're going to work out the bending moment at D there. This is point D, okay? And your bending moment is merely 13.75 kilonewtons times that distance minus 3 kilonewtons per meter times 5 meters times the distance from the centroid to there. Here you have it. HE times 5 minus 3 kilonewtons per meter times 5 meters times the distance from the center of the UDL to the top, which is a half of 5 meters, and you get a bending moment at the top, which is 31.25 kilonewton meters. And there it is, 31.25 kilonewton meters, due to this force pushing that away. You get this moment there. We said, I just illustrated the rigid joint principle, so the bending moment there is going to be 31.25, and that's why we could draw this through there with a high level of assurance that it was correct. Your bending moment for the UDL and the vertical leg is curved like that, and you could work out moments at various stations along there just to plot that curve if you wished. But the maximum would be up there somewhere at this point of minimum shear. Vertical load is a UDL, and moment diagram on ED will be curved. Now, that brings me to the end of that, and I think that's quite a simple way of doing it. I suggest you study that. I've given you some other examples, random examples. I'm not going to explain them, but they'll be food for thought for you. They show you how to work these things out for various configurations where you have different lengths of columns, different loading conditions, and you end up with all sorts of thrust diagrams, moment and shears. There you have them. You could study those. Right. Good luck with that. Thank you very much.